Welcome to the NPTEL course on integrated waste management for smart city. So, we will be doing a tutorial on the air calculations and anaerobic digestion and incineration in this session. So, now we will just look into the question number 1. So, we will to determine the amount of air supply required to compost 1 ton of municipal solid waste using an in-vessel composting system with forced aeration. So, the oxygen demand for the successive days of the 5-day composting periods have been provided in this table, and the ammonia produced during the aerobic degradation of MSW is lost to the atmosphere, and air contains 23% of the oxygen by mass, and the specific weight of the air is equal to 1.29 kilogram per meter cube, and a safety factor of 2 has been considered for the actual air supply. Then the chemical formula to be used is given over here, and we will be assuming the moisture content of the organic fraction of the municipal solid waste is 25%, and the volatile solids as 93% of the total solids, and biodegradable volatile solids BVS fraction as 60% of the volatile solids, and expected BVS conversion efficiency as 95%, and the composting time is the 5 days. Okay. And coming to the solution, the initial step of the solution, we have to calculate the total mass of biodegradable volatile solids in 1 ton of municipal solid waste. So, here the 1 ton, so we will have 1 ton. So, when we are converting it into the kg, it will be 1000 kg, 1000 kg. So, multiplied by the 0.75, this 0.75 has been arrived from the moisture content determination. So, we have 25% moisture in the municipal solid waste. So, if we just see here, the moisture content of the organic fraction of municipal solid waste is 25%. So, 100 minus 25% is the 75%, which is the dry fraction, dry matter or content, dry matter. So, that multiplied by the 0.93, the 0.93 is the volatile solids content, in multiplied by 0.60, which is the BVS fraction, So, total it will be 418.5 kg, 418.5 kg. So, next we have to determine the expected BVS conversion factor. So, the expected BVS conversion factor is the actual biological volatile solids that what we are going to get in our study. So, here we are given the expected BVS conversion efficiency as 95%. So, now we have to take the 418.5 kg, the total mass of biodegradable volatile solids, multiplied by the 0.95, we will get the actual content, that is 418.5 into 0.95, which is giving rise to 397.58 kg. 58 kg. It is the expected BVS content, So, we will be using this value in our calculations. So, in the examination, we request all the students to go for the 2 decimal precision, Now, we will be calculating the oxygen required. So, the amount of the oxygen required for anaerobic composition of 1 ton of municipal solid waste containing 397.58 kg of BVS can be estimated using the following equation. So, in the PowerPoint presentation, we can just see the equation which has been developed over here, and it has been taken from the standard literature and textbooks. So, in this already the Ca, Hb, Oc, Nd is the chemical formula, and we have been already provided with the chemical formula C74, H114, O44 and N. So, where the A will become 74 and B is equal to 114 and C is equal to 44 and D is equal to 1. So, the chemical equation for the case will be written in the format where will the molecular weight of the given chemical is 1720, and for the oxygen we have calculated 4A plus B minus 2C plus D divided by 4, we will get the molecular weight of the oxygen, where 80.75 molecules is 2584. Now, the oxygen requirement is oxygen requirement is equal to 2584 divided by 1720 into 397.58 kg, which is equal to 597.29 kg. So, we require 597.29 kg of oxygen, and now we have to calculate the amount of oxygen. After calculating the total amount of the oxygen, we will calculate the total amount of air required for 1 ton on the municipal solid waste. So, in the PowerPoint we can see the volume of air calculation over here. So, in the volume of air calculation, so we will first take the total oxygen that is there 597.29 kg. So, multiplied by safety factor. So, in the question already it has been given that the safety factor is equivalent to 2, and the total divided by the percentage of oxygen in the air, which is 23%, that is 0.23, that is the percentage of the oxygen in air multiplied by the specific weight of the oxygen, this is 1.292 kg per meter cube, which is the specific gravity. So, we will be getting 4017 meter cube, that is 4017 meter cube volume of the air, and we have been given that the air supply of the aeration system for 0.53, that is we are taking the day 2. See here the day 2 has been considered to be the critical. So, that percentage will be for 35%. So, we will multiply the air supply of the aeration required for the critical demand. So, the critical demand, the air required is equal to 4017 multiplied by 0.35 meter cube per day, which is arriving to 1406 meter cube per day. Thank you. And now we will just look into the next numerical, that is an anaerobic digester is to be designed for a dairy farm, and the dairy farm has 12 cows. Assume each cow producing 10 kg of dung daily, and the cow dung from all the cows. Now, we will design an anaerobic digester. An anaerobic digester is to be designed for a dairy farm, and the dairy farm has 12 cows. Assume each cow producing 10 kg of dung daily, and the cow dung from all the cows is available to the feedstock. This is the assumption, and assume the temperature is 30 degrees centigrade and the solid content of the cow dung is 15%, and the hydraulic retention time HRT is 45 days for the anaerobic digester, and determine the total volume of the digester for the present case, and then the diameter of the digester, the height of the digester, that is the wall. Here we will use the formula V3, that is the volume of cylindrical portion V3 of the digester can be computed by this formula. In the examination we will be providing this formula. Now, we will be calculating the total volume of the V of the digester for the present case. See here the total discharge is the 10 kg of the cow dung, that is arriving from the 12 cows, which is 120 kg per day, and the total solids of the fresh discharge will be 0.15%, that is 120 kg into 0.15, which is equal to 18 kg. Then to have the favorable condition, we will have 8% concentration of the total solids. So, now in the 8 kg of solids is equivalent to the 100 kg influent. So, 1 kg will be 100 divided by 8 kg of the influent, and for the 18 kgs it will be 100 into 18 by 8, which is equivalent to 225 kg of the influent. So, the total influent that is required is 225 kg. So, now the water to be added to make the discharge 8% concentration of the total solids we have to check out. So, it is 225 kg minus the 120 kg. So, which is equivalent to 105 kg. So, this is the total amount of the water to be added to make the discharge of 8% concentration of the total solids. And now, I have to determine the working volume of the digester. So, in the diagram you can see the different portions of the digester, where Vc is the gas collection volume. So, in the after the digestion process, once gas has been generated, it will be collected in the Vc. Then the Vg is the gas storage volume, and Vd is the active digestion volume, and Vs is the sludge layer volume. So, in the anaerobic digestion process, once in the active digestion volume, the municipal solid waste will undergo the degradation process like hydrogenesis, acidogenesis, acetogenesis and methanogenesis, and will get the gas and the sludge. The sludge will be stored in the sludge layer volume, and the gas will be storing in the gas storage volume, and it will be collected from the collection volume area. So, now we are interested in calculating the working volume, which is equivalent to the volume of the active digestion volume Vd plus Vg, that is the gas storage volume. So, which is equivalent to the flow into the hydraulic retention time. So, the flow Q is equal to the 225 kg per day, and the hydraulic retention time is provided to be the 45 days. So, multiplying this, we will get 10,125 kg, and when we are converting it into the meter cube, 1000 kg is equivalent to 1 meter cube, which is equivalent to 10.125 meter cube. And for the geometrical assumptions, we are taking Vg plus Vd is equal to 0.8 of the total volume. That we can see from the diagram, even the Vg and Vd will be covering the 80% of the anaerobic digester. So, in the geometrical assumptions, that means in the construction process, we have to take that portion geometrical assumption, which is equivalent to 0.8 of the total volume. So, the V is equal to 10.125 divided by 0.8, which is coming to 12.65 meter cube. So, this is the volume of the anaerobic digester. So, now we will calculate the diameter of the digester. So, the diameter of the digester can be directly calculated from the formula 1.3078 V raised to the volume raised to the power of 1 by 3. So, the volume has been already calculated from the previous slide, that is 12.65 meter cube. So, simply substituting this into the given formula, 1.3078 multiplied by 12.65 meter cube raised to the power of 1 by 3 will get the diameter, which is equivalent to 3.05 meter. Now, we will calculate the height of the digester. So, for calculating the height of the digester, we have V3 is equal to 3.14 into d square into h divided by 4, that is the height divided by 4. So, putting the V3 value, which has been given as 0.3142 d cube, which is equivalent to 8.89 meter cube, we will calculate the substituting this, we will get the height of the digester as 1.22 meter. Next, now we will just calculate do a numerical on the incineration. So, the Kolkata city operates a state of art volume reducing incinerator with a rocking kiln. It is currently handling 400 tons on the dry basis of semi sorted waste per day, and this is the majority of glass and metal are sorted out through the central depots. However, paper is left in the waste stream to maintain the required energy. The local authorities feel that not separating out paper gives a poor environmental image. As such, they propose a source segregation model that removes 40% of the paper content before incineration. So, neglecting the cost of collection, which will be significant, and what is the price per ton of paper that they need to receive to offset the cost of purchasing additional gas to supplement fuel. So, in the given data, we have the original mass of the paper as 45%, energy content of the paper as 16,300 kilojoule per kg, and the energy content of the natural gas as 37,300 kg per meter cube, and the cost of the natural gas as rupees 30 per meter cube. So, now initially we have to calculate the total mass of the paper for municipal solid waste containing 45% of the paper. So, we are generating 440 tons per day, out of which 0.45 45%, that is 0.45 will be the total mass of the paper. So, 440 tons per day multiplied by 0.45, we have 180 tons per day. So, the energy value from the paper is 180 tons per day into 10 meter cube per ton into 16,300 kilojoule per kg. So, which is equal to 2.93 into 10 to the power of 9 kg per day. So, the total energy value of the paper is 2.93 into 10 to the power of 9 kg per day. So, the energy loss through separation of 40% of the content. Since we are segregating the paper, so we have to remove that energy loss. So, it is 2.9 into 10 to the power of 9 kilojoule per day into 0.4. So, which is coming to 1.17 into 10 to the power of 9 kilojoule per day. So, if we are not taking this 10 power 9, in the assignments most of the students have solved with the full length calculation. It is like 1, 1, 7, 3, 4, 6, the value is coming. So, we request all the students to take this 2 decimal precision. So, it is 1.17 into 10 to the power of 9 or 2.93 for the calculations, and the energy content of the natural gas from that equation will be to calculate. So, the total amount of natural gas required to substitute the energy of the paper. So, the energy of the paper is lost is 1.17 into 10 to the power of 9 divided by the energy content of the natural gas. So, which is equivalent to 31,367 meter cube per day. So, now we have to calculate the cost of additional natural gas due to separation of the paper. So, for the amount of natural gas required to substitute the energy of the paper, that is 31,367 into the 30 will be the additional cost of the natural gas. So, which is equivalent to 9,41,010 rupees per day. So, the price per ton of the paper we have to calculate. So, the overall ton is 180 tons we are receiving in the paper form. So, for each ton, when we have to divide this 9,41,010 rupees per day divided by 180 into 0.4, that is the total paper weight, which is arriving to 13,069.58. So, rounding it off, we will get 13,070 per ton. So, in the assignment we have seen like there are few calculation mistakes, there are precision errors which have been done from our side and your side. We have calculated 2 decimal precision and the total number has been calculated by the students over there. So, which has led to different answers. So, what we suggest the students is to use the 2 decimal precision. So, to arrive this sort of answers, even in your examination, if there are the questions of this models, so you just take the 2 decimal precision and calculate to reach the required answers. So, all the best for your examinations. Thank you.